Hello, you're in a class with OPiyo for chemistry, and in this session we are going to be looking at the ionization of acids and bases, and specifically we shall start with the ionization of strong acids and strong bases, where we shall be looking at some few numericals. We have a question at hand, but before we look at that question, I want to remind you, in this context of calculation, the acids will be that substance that is capable of releasing hydrogen ions in aqueous solution. And from the previous sessions, we covered and we found out that the strong acids completely dissociates or ionize in solution to produce the hydrogen ion. So just in case you missed that, I would suggest you go and view my session on that part. On our question at hand, we are supposed to calculate the pH of 0.004 molar sulfuric acid, and that is all we need for strong acid. We just need to know the concentration. So our simplest approach here is going to be first to find out the equation of dissociation of sulfuric acid, and we know a sulfuric acid dissociates to produce 2 moles of hydrogen ions and 1 mole of the sulfate ion. Now in this calculation, the sulfate ion is of no use. We are only interested in the number of moles of hydrogen ions. So from there we can pick up the relationship in the equation that we see 1 mole of sulfuric acid produces 2 moles of hydrogen ions. So which means out of the 0.04 moles of sulfuric acid, we can produce twice that amount. So number of moles of hydrogen ions produced will be 0.08 moles. And since already it is in 1 liter, we are going to take that as the molar concentration of hydrogen ions. So we get molar concentration of hydrogen ions as 0.008 moles per decimeter cubed. And the pH of any solution is given by the negative logarithm to base 10 of molar concentration of hydrogen ions in that solution. So substituting for the molar concentration of hydrogen ions, that is the 0.008, we get pH is equal to negative logarithm to base 10 of 0.008, which gives us a value of 2.097, and that is roughly 2.1. Therefore, the pH of a 0.004 molar sulfuric acid is actually 2.1. In the next task, we are supposed to calculate the pH of a solution of 0.1 molar hydrochloric acid. Similarly, we are going to approach this by first writing the equation of dissociation, that is hydrochloric acid dissociates to produce hydrogen ions and chloride ions, and from that relationship we can find the molar concentration of hydrogen ions, since already the solution is in 1 liter. So this means since 1 mole of hydrochloric acid produces 1 mole of hydrogen ions, it implies that the molar concentration of hydrogen ions will be the same as the molar concentration of the HCl, which is 0.1 moles per decimeter cubed. And if we substitute in our pH expression, which is a negative logarithm to base 10 molar concentration of hydrogen ions, we shall be obtaining our pH value of 1.0. So which means the pH of a 0.1 molar HCl is 1.0 molar. And that is all for this question. Now in our third task, the situation has been reversed. This time we have been given the pH, and we are supposed to find the molar concentration of sulfuric acid. So we are going to reverse the calculation as well. That is, since we already know pH is given by negative log to base 10 of molar concentration of hydrogen ions, and if we divide both sides by -1, this would give us negative pH is given by log to base 10 of molar concentration of hydrogen ions. So this means molar concentration of hydrogen ions can be obtained from antilog of negative value of pH. But to put this in a calculator, you just press shift, then log, then negative that value that you want to put there, in this case negative 4.35. so this will give us the molar concentration of hydrogen ions as 4.467 exponent negative 5 moles per decimeter cubed, or molar. Then from that point we can write the equation for dissociation of sulfuric acid, producing 2 moles of hydrogen ions plus 1 mole of sulfate ions. Now, since we know the molar concentration of hydrogen ions, we are going to relate the the ratio of hydrogen ions in the equation to the one of sulfuric acid. That is, we have 2 moles of hydrogen ions are being produced by 1 mole of sulfuric acid. Now this implies that the 4.467 exponent negative 5 moles of hydrogen ions are produced by a half its mole of sulfuric acid, and we get the molar concentration of sulfuric acid as 2.3335 exponent negative 5 moles per decimeter cubed, and that is what the question actually wants. So if you're going to be calculating this, you need to know where to start from. In this very third case, we had to reverse everything because we are given the final thing. We're now supposed to calculate backwards until we find what was the concentration of that sulfuric acid. So with that, we have some numbers here to try. The first one is supposed to find the pH of 0.02 molar sulfuric acid solution in a liter, and the next one you're supposed to calculate pH of 0.01 molar HCl, and the answers are given, of course. This one will be guiding you to find out whether you have hit the right procedure or maybe you have messed along the way. I suggest you try as many times as possible in case you get stuck, and when things fail, you will always let me know your challenges on the comment section. I will be there to respond, or at the end of this video you will see there a WhatsApp number and an email where you can maybe forward your concern directly. Now we go to ionization of strong bases as well as the pH of strong bases. Now a strong base is the one which is completely ionized in aqueous solution and it easily accepts a proton. So let's consider a strong base like potassium hydroxide. It completely dissociates to produce potassium ions and hydroxyl ions. And we have pH is given by negative logarithm of molar concentration of hydrogen ions. But in this case, we don't have hydrogen ion from this ionization, which means we need to work it out. And we have a relationship that molar concentration of hydrogen ions and that of hydroxyl ions are equal to the Kw, or the ionic product of water. So which means, since our equation gives us the molar concentration of hydroxyl ions, we can use that to obtain the molar concentration of hydrogen ions given a known value of Kw. So molar concentration of hydrogen ions will be Kw divided by molar concentration of hydroxyl ions. Or if you don't do that, you could first work out the pOH, that is pOH given by negative logarithm to base 10 molar concentration of hydroxyl ions. And then if you get the pOH, then you can now go ahead and subtract it from 14, since we derived in the previous session that pH plus pOH is given by 14. So you can get the pH by subtracting pOH from 14, and that will guide you in the calculation. In either way, the answer you get must always be the same. So we have the first task at hand. We are supposed to calculate the pH of a 0.03 molar sodium hydroxide solution, given that the Kw is 1 exponent negative 14 moles squared decimeter per negative 6. So in your solution, we are going to write the dissociation or ionization of sodium hydroxide, which will give us the hydroxyl ion and sodium ion. Now, that will guide us to find the molar concentration of the hydroxyl ion. Since 1 mole of sodium hydroxide produces 1 mole of hydroxyl ion, it implies that the concentration of the hydroxyl ions will be equal to the concentration of sodium hydroxide, and we can use that to obtain the molar concentration of hydrogen ions. The molar concentration of hydrogen ion is given by Kw divided by molar concentration of hydroxyl ion. Now in this case we shall be having 1 exponent negative 14 divided by 0.03. That will give us a value of 3.33 exponent negative 12 moles per decimeter cubed. Obtaining that, we go and substitute in the pH expression, and our pH is negative logarithm to base 10 of molar concentration of hydrogen ions. And if we substitute in the value of molar concentration of hydrogen ions, we calculate and finally come with our pH being 11.477, or you can simply say your pH is 11.5. Or if you don't use that approach, getting the molar concentration of hydroxyl ion, we would first calculate the pOH by saying our pOH is given by negative logarithm to base 10 of molar concentration of hydroxyl ion. And the molar concentration of hydroxyl ion from the other side we obtain is 0.03. So substituting that 0.003, that would give us a pOH of 2.523, and our pOH can roughly be 2.5. Then after obtaining pOH, we simply substitute in our equation that pH plus pOH is given by 14, or is equal to 14. Therefore pH is going to be 14 minus pOH, and substituting for the value of pOH, which is 2.5, our pH is going to be 11.5, and that will be the pH of the 0.03 molar sodium hydroxide. So in whatever way you use, whatever approach, you must be arriving to the same value of pH. Now let's look at the second task. What we have now is calcium hydroxide, and they want us to calculate its concentration in moles per liter. If you have been given the pH as 10.61 and Kw as 1.0 exponent negative 14 molar squared. So our solution here, we are going to establish the relationship between pH and the molar concentration of hydrogen ions, which will help us to get the molar concentration of hydrogen ions. Then when we get the molar concentration of hydrogen ions, we are simply going to use the ionic product of water to help us find the molar concentration of the hydroxyl ion that is produced by calcium hydroxide at a pH of 10.6. So if we have that, using the dissociation equation or ionization equation of calcium hydroxide, we can relate the molar concentration of hydroxyl ion with that of calcium hydroxide, so that we obtain the concentration of calcium hydroxide at that pH. So our first thing there is to get the pH as negative logarithm to base 10 of hydrogen ions, and therefore the hydrogen ion concentration will be antilog of pH of negative pH, which is actually shift plus log of negative pH on a calculator, and this will give us the molar concentration of hydrogen ion as 2.455 exponent negative 11 moles per decimeter cubed, or molar. And now that we have the molar concentration of hydrogen ions, we should remember that molar concentration of hydrogen ions times molar concentration of hydroxyl ion is given by 1 exponent negative 14. Therefore, molar concentration of hydroxyl ion will be 1 exponent negative 14 divided by molar concentration of hydrogen ions. So if we substitute for that value, we obtain the molar concentration of hydroxyl ion as 4.073 exponent negative 4 moles per decimeter cubed. So now that we have the molar concentration of hydroxyl ion, we can go ahead and write the dissociation equation for calcium hydroxide. And calcium hydroxide, once it is dissolved, it will be giving us 1 mole of calcium ion and 2 moles of hydroxyl ion. Now the calcium ion is of no interest to us in this calculation, but the hydroxyl ion. Then from that equation, we can clearly relate that 2 moles of the hydroxyl ions are produced by 1 mole of calcium hydroxide. So this implies that 4.073 exponent negative 4 moles of hydroxyl ions are produced by a half the moles of that hydroxyl ion for the calcium hydroxide ion. So the number of moles of calcium hydroxide ion will be half that of the hydroxyl ions. And since the molar concentration of hydroxyl ion is already in liter, we only need to conclude that the molar concentration of calcium hydroxide is 2.037 exponent negative 4 moles per decimeter cubed. That is approach 1. Now, if you are not to use that in our second approach, what you would do would just be so if we don't use this approach, what we can do is to first, I've not shown that on the slide, but what you can do is you get the pH, which is 10.61, you subtract it off from 14, because pH plus pOH is equal to 14. So pOH would be 14 minus 10.61. So if you put that value into your calculator, you have 14 minus 10.61. It would give you pOH value of 3.39. And the pOH is given by negative logarithm to base 10 of molar concentration of hydroxyl ion. So if you divide both sides by -1, you get logarithm to base 10 of molar concentration of hydroxyl ion is given by negative pOH, which is negative 3.39. So for you to obtain the molar concentration of hydroxyl ion, it will now be the antilog or shift plus log of negative 339. And if you get that, shift log negative of 3.39. That would give you molar concentration of hydroxyl ion as 4.07 for exponent negative 4 moles per decimeter cube, which is the same as what we obtain in the first method. So after obtaining that, you are going to follow the same procedure, write the equation for ionization of calcium hydroxide, relate the hydrogen ions to calcium hydroxide for you to obtain the molar concentration of calcium hydroxide. So that brings us to the end of this part, calculation of pH of strong bases. But I have some work that you can try out during your free time. Now we have the first question. There is 25 cubic centimeters of 0.3 molar sodium hydroxide was added to 225 cubic centimeters of water. You're supposed to calculate the pH of the resultant solution, and the answer you will obtain there is 12.477 or just 12.5. And number 11 is telling you to calculate the pH of the following solutions: 3 exponent negative 3 moles per decimeter cube of calcium hydroxide, and 0.5 molar sodium hydroxide, 2.5 exponent negative 2 molar sodium hydroxide, 0.01 molar potassium hydroxide. Now in all cases, the value of Kw is 1 exponent negative 14 mole squared decimeter power negative 6. Thank you so much for your time. I'm really glad you followed up this session, and if you have followed up this session up to the end, you are really not regretting your time with me. I would like to urge you to kindly subscribe to my channel for further engagement in different sessions, and turn on the notification bell so that the next time I upload a new video, you are informed and you don't miss a single session. And if you have any concern, or if the numbers I've put for you become tough, you can easily forward them on WhatsApp so that I guide you on how to solve them, or you can email me on that email on the screen, that is gmailopio@gmail.com. I hope to see you next time. Thank you very much, but please subscribe.